Sound waves are density waves traveling through the medium of air. When we talked about the harmonics on an open-ended tube, instead of representing that density by actually drawing out the particles of air, we went with this convention of representing this as a high density area, this is a low density area, this is a high density, low density, and graphing that out so that we graphed high density, low density, high, low, high, low, high, low, high, and we could keep the same kind of pictures and convention that we had for waves on a string. We are going to continue this method of representing sound waves and as air density waves as a density versus position graph when we're talking about closed-ended tubes. So this was an open-ended tube, and in the open-ended tube, we could see that there is an antinode at this end and an antinode at this end. When we're dealing with a closed-ended tube, one end is going to be an antinode, but the other end of the tube, let's put the end right here, the other end of this tube is going to be a node. The reason why we have that is because the open end of the tube, which is open to air, the open end of the tube, the air is free to vibrate back and forth. But on the closed end of the tube, it is not free to vibrate back and forth. And it's more similar to when we had waves on a string and the end of the string was not free to vibrate. So the end of the closed end of the tube has to be a node and the open end has to be an antinode. Once we recognize that that is going to be the case, drawing which waves resonate on a tube becomes more simple. I'm going to redraw a couple of tubes here. Here's one. Here's the second one. And here's a third one. This first wave here, this first tube, here is the open end, so that's going to have an antinode. And here is the closed end, so that's going to have a node. The longest wave that can resonate on here will just have the part of the wave that corresponds to the distance between one antinode and one node. It then bounces off this wall and comes back looking just like this. We're going to figure out in a minute what part of a wave that is, what percentage of a wave that really is. The second and third waves that can resonate will also have an antinode on this end and a node on this end. Now, the second longest wave would also have to have another set of antinodes in it. And if they're going to have another set of antinodes, it's going to have another node. So the next longest wave, the second longest wave that can resonate in here, would look like this. It's going to reflect off this wall and come back. And we can go through the same process for the third longest wave that can resonate on this tube. It's going to have a node at this end, an antinode at the open end, so it's going to have two additional sets of antinodes. And two additional nodes. And when we draw this wave, it's going to look like this. You can continue this pattern in your notes for the next wave. All right, so we know that if we were to draw one wavelength, we would draw it like this. Well, there's a couple of ways you could draw, but we need to show that it has a complete cycle where it starts in any particular position and goes through the whole wave. If we're trying to figure out what part of a wave does this represent, we could break this down and say, well, what does that look like? It's from a highest point to a middle point. From a highest point to a middle point. This is also from a highest point to a middle point. This is from a middle to a low lowest point, which is kind of like the inverse of that, and this is from a lowest point to a middle point. Each one of these is a quarter of the total, 1/4 of the total. So we can see right here that this tube, length L, this top one, this length L represents 1/4 of the wavelength. So the wavelength has to then be 4 times the length of that tube. We can go through the same kind of analysis for this second wave here. That's 1/4 of a wave. That's 1/4 of a wave. That's 1/4 of a wave. To determine that 3/4 of a wave are in this tube. That means that this wavelength is 4/3 the length of this tube. Here we have 1/4 of a wave, 1/4 of a wave, 1/4 of a wave, 1/4 of a wave. So we have a whole wave filling up less than the tube. That means that the wavelength of this is 4/5 the length of this tube. This tube is in 5 sections, 1, 2, 3, 4, 5, and the wave takes up 4 of them. In a similar way to how we derived a formula for the wavelength of a particular harmonic in terms of the length of the tube, we can do the same thing for this wave, for this closed-ended tube. What we're going to find, if we actually follow this and said this is the first, this is the second, this is the third harmonic, we would get a particular relationship. If we then went through the process of saying, well, velocity equals frequency times wavelength, and we found the frequency for each, we would find that these frequencies are not multiples of each other in the same way that an open-ended tube, in the same way that the harmonics on an open-ended tube are, and in the same way that the harmonics on a string are. We would find that the frequency for this and the frequency for this, the second wave here, the second longest wave that can resonate on this tube, is not double the frequency of that on the first. We find that it's 3 times. As a result, what we're determining here is that this is not the second harmonic. We wind up finding that this is the third harmonic and this is the fifth harmonic. When we write out an equation for what's the relationship between, or what's the equation for the wavelength of a particular harmonic, we find that the wavelength of the nth harmonic on a closed-ended tube is 4L over n, as opposed to 2L over n for an open-ended tube. But we furthermore find out that n can't just be any positive integer. In the case of a closed-ended tube, n can only equal odd positive integers. So 1, 3, 5, 7,